Hi everybody, welcome back to Physics Screencasts. Today what we're going to do is work our way through three different types of vector addition problems, each one of which is going to teach us something important about the way we deal with questions involving vectors. So we're going to jump right into it here and notice that the first question has to do with a pilot who's flying north at 175 kilometers an hour while being blown east at 25 kilometers an hour. Because that's all they tell us in this problem, this is a dumb pilot question. This sounds like a pilot who's intending to fly north that's getting blown east and is kind of all good with it. Not like most pilots I know who tend to be pretty uptight about landing their planes at airports. So anyway, here's the deal. What we just did was draw one arrow that represented 175 kilometers an hour and another arrow that represented 25 kilometers an hour. And the way we did it was we started out at a home base, took the long arrow and drew it out of that home base heading north, and then just like we talked about in class, we then headed out of the end of that first arrow and added on our second arrow. And you notice that we've got the directions right. Both of these things are pretty much to scale. We've got at least a long arrow and a short arrow, and we've got labels that are all the same, which is important when we're adding. So the next thing that we're going to do, now that we've got our arrows added together like they're one-way streets, is to draw in the answer arrow, the resultant. And like we said in class again, the answer arrow is the arrow that cuts from our home base down here up to the place we ended up when we were done driving our one-way streets. So the idea is that you think about this answer arrow as being the way that a bird could fly. Whereas if you were in a car, you might have to go down this street and then drive to that street. So what we're going to do is use our two math tactics that we've talked about. We're going to use some Pythagorean theorem. We're going to call this the resultant over there, but he's really the hypotenuse. So I know that the resultant squared equals 175 squared plus 25 squared. And we'll do a little bit of math and figure out that C equals 177, and since the labels were all the same, we can just paste that label on right there. So C is 177 kilometers per hour. Now, the next thing we're going to do is we're going to dial up the inside angle of the triangle and call that angle theta. And since we have all three parts of the triangle, we can do any kind of trig that we want. I'm kind of a fan of just using the ones that were provided in the problem because there's never any issues with rounding, and that's how I get the answers that you'll see on the worksheets. We just do it that way. So if I have this side up here and this side right here, compared to this angle theta I just drew, this is the opposite side right here, and this guy would be the adjacent side right there. And so I know that the trig function that uses the opposite and the adjacent is the tangent. So what I'm going to do is write this trig formula down. Tangent of theta equals opposite over adjacent, and then solve using an inverse trig function to find the angle. So we're just going to go grab a calculator and do that and get right back to you. Okay, so when I'm done plugging away on my calculator, I find that that angle, theta, is around 8 degrees. Now, what I'm going to do is just wipe this screen mostly and go and show you one really important thing that sometimes causes people trouble. So hang on there and we'll be right with you. Alright, so here we go. One of the biggest issues that people run into when they're trying to figure out directions on the compass is that if we know that the angle on the inside of my triangle here is 8 degrees, what we need to find out is what compass angle are we on. And we're using the system in class that says that 0 degrees is the angle that points straight out east. And our system says that the way you do this is you spin counterclockwise from 0 degrees, and then that angle right there, the one that I just drew, is the answer angle. And so there are usually two right ways to think about this. You could visualize that you're going to draw the answer angle all the way to 90 and then back off by 8 degrees, in which case you end up with 82, or you could just think of it as what angle is 8 degrees shy of 90. So either way you slice it, the answer angle in this case is going to turn out to be 90 minus 8, or 82 degrees. And so the overall answer, what you want to tell folks, is the resultant is going to be 177 kilometers per hour at an angle of 82 degrees, and that's all the information that you need to provide to have a complete answer. So we'll practice that one more time, and you'll see we'll do it with a little bit of a twist, but you'll get to see this skill happen in just a second. So here you go. Okay, so we've seen a dumb pilot question. Let's go check out this one and see how it's different. In this question, we've got a pilot who's heading 240 kilometers an hour to the south, and there's a crosswind that acts on him that's blowing 25 kilometers an hour to the east. And how is this different from the dumb pilot question? We'll just check it out. What they're asking us now is how should this guy fly in order to reach a point that's due south. Alright, so that's the difference. This person has an actual destination, maybe an airport, and what they're going to try to do is head there. So we can sketch this out just like we did the last example. We notice that the units are compatible, which is great. We have an arrow now that's going to point 240 kilometers an hour to the south. And as soon as I write that arrow, as soon as I write that very first arrow, what I need to remember is that I've already committed to what I think is the home base for the problem. So I always shift gears without saying so between planes and everything else and cars. But what I'm going to visualize is that I'm driving down south now, away from my house, and that what's going to happen is I'm going to be pushed east, like so. And what I've tried to do is make these arrows at least a little bit to scale. So I've got a long one, and I've got one that's a lot shorter. And then we have a vector picture that's a lot like the last one. So the answer would be, if we were flying south and we were going to be blown to the east, we would end up with our resultant arrow that starts from home base up here and ends down at our ending point, just like a bird would do. So that would be the answer to the question if this was a dumb pilot question. But what we're going to do is actually something that pilots, real pilots, are used to doing a lot. They understand this intuitively. What happens is that we have to actually point the airplane a little bit in the opposite direction. And what I mean by that is whatever the wind does, you as the pilot have to undo. And so what we're going to do is say, never mind, we're not the dumb pilot. We're not going to head in that direction and be blown off course heading out this way. What in fact we're going to do is point the airplane in this direction so that when it hits or is hit by this very real wind that's pushing us to the east, what we're in fact going to do is end up flying straight south, just like we wanted to. And so the math is going to be a lot the same as the last one. We've got 25 kilometers per hour. We're going to do the same kind of math as we did in the last example, but it's going to be flipped around backwards. So we're going to go ahead and use the same exact tricks we used last time. 240 kilometers an hour belongs on this one. The resultant arrow is there. It's the long one. It's what I always call side C. So C squared equals 240 squared plus 25 squared. And Pythagoras is going to, when we crank that out, it's going to tell us that the hypotenuse is 241 kilometers per hour. And then what we're going to do is find the little wedge angle between home base and the first arrow. And if I look there, then I know that I'm going to have the opposite side of the triangle down here is 25. The adjacent side here is 240. And then that's going to say to me that I can use the tangent. So tangent of theta equals 25 over 240. And then when I go ahead and get tangent inverse on my calculator, like so, it's going to go and tell me when I pull the handle that I get an angle of 6 degrees for angle of theta. Alright, so knowing that I have angle theta equals 6 degrees, what I'm going to do is, just like last time, I'm going to try to I'll create a little more space here and X out some of this stuff that I've done. So hold on a second here. And we'll get that one, get that one. One more time. There we go, got that. And I just want to think out loud about, if I know that this angle right here is 6 degrees, how do I deal with the compass angle? So again, the big thing to know is that I'm going to start realizing that east is 0 degrees, and that the answer arrow that I have drawn right here is in the 1, 2, 3rd quadrant. And so my job is to go ahead and take this whole thing and work it around counterclockwise until I hit my answer arrow. So one of the ways I talk about it is if you visualize lifting up this answer arrow right here, starting it so that it points east out this way, and spinning it all the way around until it points there, then you will have done the right number of degrees. So if you count the quadrants, it makes it a lot easier. So we'll start at 0 degrees here, spin through 90, spin through 180, and the answer arrow wants to point at 180 plus whatever this big thing is right here. So if I just think for a minute, I know what that big thing is. This angle right here plus 6 equals 90. So the angle must be 84 degrees. So 180 right here plus 84 would get me the right answer. And again, another way to look at it, similar to what we talked about last time, is if I wanted to spin the answer angle all the way down to 270 and then back it off by 6 degrees, that would be the same thing. And so either way you slice it, what I'm going to end up with is that the answer is going to be 241 kilometers per hour at an answer angle of 264 degrees. And there you go. So the last question we're going to take a look at today is question number 4 from A-48. And this one's important because it gives us a chance to visit with some of the skills we've been talking about, but also gives us a chance to talk about one super important fact that lies underneath all of vectors. So to jump in, it looks like we've got a boat that's headed north, and he's being pushed east at the same time. And since that's all they tell us, this kind of reminds me of the dumb pilot question. So this is sort of like the dumb boat driver question. What we've got now is an arrow that I pointed north that represents my 4.5 meters per second. And again, you should know, as soon as you draw that first arrow, you've already committed to where your home base is going to be located. And it's located right here at the tail of the very first arrow. That's where you came from. So then from there, we're going to draw a shorter arrow that represents my 1.6 meters per second, like so. And then again, the resultant arrow is the one that gives us the shortcut, the way the bird would fly, from home base to where we ended up driving in our car along those one-way streets. So R is going to be, thanks to Mr. Pythagoras, the square root of 1.6 squared plus 4.5 squared, and that turns out to be 4.78 meters per second. And again, I'm able to put that label right on there because the labels I had going into the problem were compatible with each other. The next thing I'm going to do is write down angle theta, like so. And I know that I have up here the opposite side of the triangle from theta as 1.6, and the adjacent right there is 4.5. So I'm going to pick the tangent function to use, 1.6 over 4.5, and I'm going to find out that the tangent of that angle means that the angle works out to be 20 degrees. So we're just going to go ahead and finish this off and talk about the very last skill we've been discussing, which is to remember that if this line out here of east represents 0 degrees, our answer angle is going to be the angle that brings us from 0 degrees out to here. And it looks to me like if we're 20 degrees short of 90, so if we took our answer resultant angle up here and then backed it off by 20, then we'd be pointing in the right direction. And that, to me, tells us that the overall answer is 4.78 meters per second at 70 degrees. So we're 70 degrees from 0 right there. Okay, so what we need to do is make a little bit of space and now talk about that very important thing that underlies all the vectors. So hang on there. Okay, so questions B and C give us a chance to talk about the very important thing that I was alluding to. What question B says, asks us is, if the channel is 3,400 meters wide, how long does it take you to cross the river? So crossing the river sounds like this is what you're trying to do. You're trying to head at 4.5 meters per second. But you might really wonder, well, what am I supposed to do with this? This is 4.78 meters per second. Isn't that the guy's actual speed? And this is where I'm going to say a very important fact about vectors and about the real world, but you're going to see us demo this in class a couple of different ways. Here's the fact, I'll tell you, and I'll just use it. The fact is that there's only one piece of this triangle that could possibly get us towards the shore that's over here, and that is this 4.5 meter per second. The actual fact is that this 4.78 meters per second number, when I break it down, has two things inside of it. It has a sideways component of 1.6, and it has this component right here. And so if what I'm doing is talking about getting across a stream that's 3,400 meters wide, that's asking me only about things that are headed in this direction. So what I do is I match up like things with like things, and I don't have to use any fancy math at all. There's no averaging, there's just distance equals speed times time. This boat is traveling at a steady speed of 4.5 meters per second in the right direction. Now it so happens he is being blown off course, but we're not worried about that. Just because 3,400 meters wide doesn't worry about that. So the math for B and C are very similar. They're really just this simple. 3,400 meters equals 4.5 meters per second times how long does it take him to get across the stream, and I find out that that is a long time. T equals 756 seconds. So there you go. Now what you're going to do is use the same kind of thinking on question C. So let's create a little bit of space here, and we'll go do that. And question C is going to say how far down the channel will the current carry you in that time. So the down the channel piece looks like 1.6 meters per second. That's the part that's going to be the part that blows me off course. And so I have, again, distance equals speed times time. And what I'm thinking of is 1.6 meters per second times how long am I going to be in the water as I try to go across this river. And I combine those two things, and I find out that it's a long way. I'm going to end up over 1,000 meters off course. But there you go. That's how that question plays out. Remember, if what you're trying to do is head in this direction, it's only this part of the triangle that can get you there. And if what you're doing is talking about how far this way do you go, that's fine. This is the only part of the triangle that can get you there. So there you go. See you soon. Have a nice day. Bye-bye.